Hello and welcome. My name is Alan, and today we are back with more ideas and opinions from Albert Einstein. Today's piece is a long one. It's called Geometry and Experience. Lecture before the Prussian Academy of Sciences, January the 27th, 1921. The last part appeared first in a reprint by Springer, Berlin, 1921. This is a long one, so let's just get into it. One reason why mathematics enjoys special esteem above all other sciences is that its propositions are absolutely certain and indisputable, while those of all other sciences are to some extent debatable and in constant danger of being overthrown by newly discovered facts. In spite of this, the investigator is another department of science would not need to envy the mathematician if the propositions of mathematics referred to objects of our mere imagination and not to objects of reality, for it cannot occasion surprise that different persons should arrive at the same illogical conclusion when they have already agreed upon the fundamental propositions, axioms, as well as the methods by which other propositions are to be deduced therefrom. But there is another reason for the high repute of mathematics, in that it is mathematics which affords the exact natural sciences a certain measure of certainty to which, without mathematics, they could not attain. At this point, an enigma presents itself which in all ages has agitated inquiring minds. How can it be that mathematics, being after all a product of human thought which is independent of experience, is so admirably appropriate to the objects of reality? Is human reason, then, without experience, merely by taking thought, able to fathom the properties of real things? In my opinion, the answer to this question is, briefly, this. As far as the propositions of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. It seems to me that complete clarity as to this state of reality, or this state of things, become common property only through that trend in mathematics which is known by the name of axiomatics. The progress achieved by axiomatics consists in it having neatly separated the logical form from its objective or intuitive content. According to axiomatics, the logical form alone forms the subject matter of mathematics, which is not concerned with the initiative or other content associated with the logical formal. Let us for the moment consider that the point of view any axiom of geometry for existence the following. Through 2 points in space there always passes one and only one straight line. How is this axiom to be interpreted by the older sense and in the more modern sense? The older interpretation, everyone knows that a straight line is and what a point is. Whether this knowledge springs from an ability of the human mind or from experience from some cooperation of the two or from some other source is not for the mathematician to decide. He leaves the question to the philosopher. Being based upon this knowledge, which precedes all mathematics, the axiom stated above is, like all other axioms, self-evident. That is, it is the expression of a part of this priori knowledge. The more modern interpretation, geometry, treats of objects which are denoted by the words straight, line, point, etc. No knowledge or intuition of these objects is assumed, but only the validity of the axioms, such as the ones stated above, which are to be taken in a purely formal sense, i.e., as void of all content of intuition or experience. These axioms are free creations of the human mind. All other propositions of geometry are logical inferences from the axioms, which are to be taken in the nominalistic sense only. The axioms define the objects of which geometry treats. Schlick, in his book on epistemology, has therefore characterized axioms very aptly as implicit definitions. This view of axioms, advocated by modern mathematics, purges mathematics of all extraneous elements, and thus dispels the mystic obscurity which formerly surrounded the basis of mathematics. But such an expurgated exposition of mathematics makes it also evident that mathematics, as such, cannot predicate anything about objects of our intuition or real objects. In axiomatic geometry, the words point, straight line, etc. stand only for empty conceptual schemata. That which, given them context, is not relevant to mathematics. Yet, on the other hand, it is certain that mathematics generally, and particularly geometry, owes its existence to the need which was felt of learning something about the behavior of real objects. The very word geometry, which, of course, means earth measuring, proves this. For earth measuring has a lot to do with the possibilities of the disposition of certain natural objects which respect to one another, namely with parts of the earth, measuring lines, measuring wands, etc. It is clear that the system of concepts of axiomatic geometry alone cannot make any assertions as to the behavior of real objects of this kind, which we will call practically rigid bodies. To be able to make such assertions, geometry must be stripped of its merely logical formal character by the coordination of real objects of experience within the empty conceptual schemata of axiomatic geometry. To accomplish this, we need only add the proposition solid bodies are related with respect to their possible dispositions as are bodies in Euclidean geometry of 3 dimensions. Then the proposition of Euclid contain affirmation as to the behavior of practically rigid bodies. Geometry thus completed is evidently a natural science. We may in fact regard it as the most ancient branch of physics. Its affirmations rest essentially on induction from experience, but not on logical inferences only. We will call this completed geometry, practical geometry. and shall distinguish it in what follows from purely axiomatic geometry. The question whether the practical geometry of the universe is Euclidean or not has a clear meaning, and its answer can only be furnished by experience. All length measurements in physics constitute practical geometry in this sense, so too do geodetic and astronomical length measurements. If one utilizes the empirical law that light is propagated in a straight line, and indeed in a straight line in the sense of practical geometry. I attach special importance to the view of geometry which I have just set forth, because without it I should have been unable to formulate the theory of relativity. Without it, the following reflection would have been impossible. In a system of reference rotating relatively to an inertial system, the laws of disposition of rigid bodies do not correspond to the rules of Euclidean geometry on account of Lorentz contraction. Thus, if we admit non-inertial systems on an equal footing, we must abandon Euclidean geometry. Without the above interpretation, the decisive step in the transition to generally covariant equations would certainly not have taken. If we reject the relation between the body of axiomatic Euclidean geometry and the practically rigid body of reality, we readily arrive at the following view, which was entertained by that acute and profound thinker H. Poincaré. Euclidean geometry is distinguished above all other conceivable axiomatic geometries by its simplicity. Now, since axiomatic geometry by itself contains no assertions as to the reality which can be experienced, what can do so only in combination with physical laws, it should be possible and reasonable, whatever may be the nature of reality, to obtain Euclidean geometry. For if contradictions between theory and experience manifest themselves, we should rather decide to change physical laws than to change axiomatic Euclidean geometry. If we reject the relation between the practically rigid body and geometry, we shall indeed not easily free ourselves from the convention that Euclidean geometry is to be retained as the simplest. Why is the equivalence of the practically rigid body and the body of geometry, which suggests itself so readily, rejected by Poincaré and other investigators? Simply because under closer inspection and real solid bodies in nature are not rigid, because their geometrical behavior, that is, their possibility of relative disposition, depend upon temperature, external forces, etc. Thus, the original, immediate relation between geometry and physical reality appears destroyed, and we feel impelled toward the following more general view, which characterizes Poincaré's standpoint. Geometry predicates nothing about the behavior of real things, but only geometry, together with the totality of physical laws, can do so. Using symbols so that we may say that the only sum of geometry, G, and the reality of physical laws, P, added together, is subject to experimental verification. Thus, G may be chosen arbitrarily, and also parts of P. All these laws are conventions. All that is necessary to avoid contradictions is to choose the remainder of P so that G and the whole of P are together in accord with experience. Envisioned in this way, axiomatic geometry and the part of natural law which has been given a conventional status appear as epistemologically equivalent. Subspecie aeterni poincare, in my opinion, is right. The idea of the measuring rod and the idea of the clock coordinated with it in theory of relativity do not find their exact correspondence in the real world. It is also clear that the solid body and the clock do not, in the conceptual edifice of physics, play the part of irreducible elements, but that the composite structures, which must not play any independent part in theoretical physics, but it is my conviction that in the present stage of development of theoretical physics, these concepts must still be employed as independent concepts, for we are all still too far from possessing such certain knowledge of theoretical principles of atomic structure as to be able to construct solid bodies and clocks theoretically from elementary concepts. Further, as to the objection that there are no reality rigid bodies in nature, and that therefore the properties predicated of rigid bodies do not apply to physical reality, this objection is by no means so radical as might appear from a hasty examination, for it is not a difficult task to determine the physical state of a measuring body so accurately that its behavior relative to other measuring bodies shall be sufficiently free from the ambiguity to allow it to be substituted for the rigid body. It is to measuring bodies of this kind that statements about rigid bodies must be referred. All practical geometry is based upon the principle which is accessible to experience and which we will now try to realize. Suppose two marks have been put upon a practically rigid body. A pair of two such marks we shall call a tract. We imagine two practically rigid bodies, each with a tract marked out on it. These two tracts are said to be equal to one another if one marks of the one tract can be brought to coincide permanently with the marks of the other. We now assume that if the two tracts are found to be equal once and anywhere, they are equal always and everywhere. Not only the practical geometry of Euclid, but also its nearest generalization, the practical geometry of Riemann, and therefore the general theory of relativity, rest upon this assumption. Of the experimental reasons which warrant this assumption, and will mention only one, the phenomenon of the propagation of light in empty space assigns a tract, namely the appropriate path of light, to each interval of local time, and conversely. Thence it allows that the above assumption for tracts must hold good for intervals of clock time in the theory of relativity. Consequently, it may be formulated as follows. The two ideal clocks are going at the same rate at any time and at any place, being then an immediate proximity to each other, they will always go at the same rate, no matter where and when they are again compared with each other at one place. If this law were not valid for natural clocks, the proper frequencies for the separate atoms of the same chemical element would not be in such exact agreement as experience demonstrates. The existence of sharp spectral lines is a convincing experimental proof of the above-mentioned principle of practical geometry. This is the last analysis. In the last analysis is the reason which enables us to speak meaningfully of a Riemannian metric for the four-dimensional space-time continuum. According to the view advocated here, the question whether this conundrum has a Euclidean, Riemannian, or any other structure is a question of physics proper which must be answered by experience and not a question of a convention to be chosen on the grounds of mere expediency. Riemann's geometry will hold if the laws of disposition of practically rigid bodies approach those of Euclidean geometry, the more closely the smaller the dimensions of the region of space-time under consideration. It is true that the proposed physical interpretation of geometry breaks down when applied immediately to spaces of submolecular order of magnitude, but nevertheless, even in questions as to the constitution of elementary particles, it retains part of its significance. For even when it is a question of describing the electrical elementary particles constituting matter, the attempt may still be made to ascribe physical meaning to those field concepts which have been physically defined for the purpose of describing the geometrical behavior of bodies which are large as compared with the molecule. Success alone can divide us as to the justification of such an attempt, which postulates physical reality for the fundamental principles of Riemann's geometry outside of the domain of their physical definitions. It might possibly turn out that this extrapolation has no better warrant than the extrapolation of the concept of temperature to the parts of a body of molecular order of magnitude. It appears less problematic to extend the concepts of practical geometry to spaces of cosmic order of magnitude. It might, of course, be objected that a construction composed of solid rods departs the more from ideal rigidity of the greater its spatial extent. But it will hardly be possible, I think, to assign fundamental significance to this objection. Therefore, the question whether the universe is spatially finite or not seems to me an entirely meaningful question in the sense of practical geometry. I do not even consider it impossible that this question will be answered before long by astronomy. Let us call to mind that the general theory of relativity teaches in this respect. It offers two possibilities. One, the universe is spatially infinite. This is possible only if the universe, the average spatial density of matter concentrated in the stars, vanishes, i.e., if the ratio of the total mass of the stars to the volume of the space through which they are scattered indefinitely approaches zero as greater and greater volumes are considered. 2. The universe is spatially finite. This must be so if there exists an average density of the ponderable matter in the universe which is different from zero. The smaller that average density, the greater is the volume of the universe. I must not fail to mention that a theoretical argument can be adduced in favor of the hypothesis of a finite universe. The general theory of relativity teaches us that the inertia of a given body is greater as there are more ponderable masses in proximity to it. Thus, it seems very natural to reduce the total inertia of a body to interaction between it and the other bodies in the universe, as indeed, ever since Newton's time, gravity has been completely reduced to interaction between bodies. From the equations of the general theory of relativity, it can be deduced that this total reduction of inertia to interaction between masses, as demanded by E. Mach, for example, is possible only if the universe is spatially finite. Many physicists and astronomers are not impressed by this argument. In the last analysis, experience alone can decide argument. In the last analysis, experience alone can decide which of the two possibilities is realized in nature. How can experience furnish an answer? At first, it might seem possible to determine the average density of matter by observation of that part of the universe which is accessible to our observation. This hope is illusory. The distribution of the visible stars is extremely irregular, so that we on no account may venture to set the average density of star matter in the universe equal to, let us say, the average density in the galaxy. In any case, however great the space examined may be, we could not feel convinced that there are any more stars beyond that space. So it seems impossible to estimate the average density. But there is another road, which seems to be, to me, more practicable, although it also presents great difficulties. For if we inquire into the deviations of the consequences of the general theory of relativity which are acceptable to experience from the consequences of the Newtonian theory, we first of all find a deviation which manifests itself in close proximity to gravitating mass, and has been confirmed in the case of the planet Mercury. But if the universe is spatially finite, there is a secure deviation from Newtonian theory, which, in the language of the Newtonian theory, may be expressed thus: the gravitational field is such as if it were produced not only by the ponderable masses, but in addition to the mass density of negative sign distributed uniformly throughout space. Since its fictitious mass density would have to be extremely small, it would be noticeable only in very extensive gravitating systems. Assuming that we know, let us say, that the statistical distribution and the masses of the stars in the galaxy, then by Newton's law we can calculate the gravitational field and the average velocities which the stars must have, so that the galaxy should not collapse under the mutual attraction of its stars, but should maintain its actual extent. Now, if the actual velocities of the stars which can be measured were smaller than the calculated velocities, we should have a proof that the actual attractions of great distances are smaller than by Newton's law. From such a deviation, it could be proved indirectly that the universe is finite. It would even be possible to estimate its spatial dimensions. Can we visualize a three-dimensional universe which is finite yet unbounded? The usual answer to this question is no. But that is not the right answer. The purpose of the following remarks is to show that the answer should be yes. I want to show that without any extraordinary difficulty, we can illustrate the theory of a finite universe by means of a mental picture to which, with some practice, we shall soon grow accustomed. First of all, on observation of epistemological nature, a geometrical physical theory as such is incapable of being directly pictured, being merely a system of concepts. But these concepts serve the purpose of bringing a multiplicity of real or imaginary sensory experiences into connection in the mind. To visualize a theory, therefore, means to bring to mind the abundance of sensible experiences for which the theory supplies the schematic arrangement. In the present case, we have to ask ourselves how we can represent that behavior of solid bodies with respect to their mutual disposition contact, which corresponds to the theory of a finite universe. There is really nothing new in which I have to say about this, but innumerable questions addressed to me prove that the curiosity of those who are interested in the matters has not yet been completely satisfied. So will the initiated please pardon me, in that part of what I shall say has long been known. What do we wish to express when we say that our space is infinite? Nothing more than we might say, then we might lay any number of bodies of equal sizes side by side without ever filling space. Suppose that we are provided with a great many cubic boxes, all of the same size. In accordance with Euclidean geometry, we can place them above, beside, and behind one another so as to fill an arbitrarily large part of space. But this construction would never be finished. We could go on adding more and more cubes without ever finding that there was no more room. That is what we wish to express when we say that space is infinite. It would be better to say that space is infinite in relation to practically rigid bodies, assuming that the laws of disposition for those bodies are given by Euclidean geometry. Another example of an infinite continuum is the plane. On a plane surface, we may lay squares of cardboard so that each side of any square has the side of another square adjacent to it. The construction is never finished. We can always go on laying squares. If their laws of disposition correspond to those of plane figures of Euclidean geometry, the plane is therefore infinite in relation to the cardboard squares. Accordingly, we say that the plane is an infinite continuum of 2 dimensions and space an infinite continuum of 3 dimensions. What is here meant by the number of dimensions, I think I may assume to be known. Now, we take an example of a 2-dimensional continuum which is infinite, or which is finite, but unbounded. We imagine the surface of a large globe and a quantity of small paper discs, all of the same size. We place one of the discs anywhere on the surface of the globe. If we move the disc about anywhere we like on the surface of the globe, we do not come upon a boundary anywhere on the journey. Therefore, we may say that a spherical surface on the globe is an unbounded continuum. Moreover, the spherical surface is a finite continuum. For if we stick the paper discs on the globe so that no disc overlaps another, the surface of the globe will finally become so full that there is no room for another disc. This means exactly that the spherical surface of the globe is finite in relation to the paper discs. Further, the spherical surface is a non-Euclidean continuum of 2 dimensions. That is to say, the law of disposition for the rigid figures can be shown in the following way. Take a disc and surround it in a circle by 6 more discs, each of which is to be surrounded in turn by 6 discs, and so on. If this construction is made on a plane surface, we obtain an uninterrupted arrangement in which there are 6 discs touching every disc except those which lie on the outside. On the spherical surface, the construction also seems to promise success at the outset, and that the smaller radius of the disc in proportion to that of the sphere, the more promising it seems. But as the construction progresses, it becomes more and more patent that the arrangement of the discs in the manner indicated without interruption is not possible as it should be possible by Euclidean geometry of the plane. In this way, creatures which cannot leave the physical surface and cannot even peep out from the spherical surface into 3-dimensional space might discover merely by experimenting with discs that their 2-dimensional space is not Euclidean but spherical space. From the last results of the theory of relativity, it is probable that our 3-dimensional space is also approximately spherical. That is to say that the laws of disposition of rigid bodies in it are not given by Euclidean geometry, but approximately by spherical geometry, if only we consider parts of space that are more sufficiently extended. Now, this is the place where the reader's imagination boggles. Nobody can imagine this thing, he cries indignantly. It can be said, but cannot be thought. I can imagine a spherical surface well enough, but nothing analogical to it in 3 dimensions. We must try to surmount this barrier in the mind, and the patient reader will see that it is by no means a particularly difficult task. For this purpose, we will first give our attention once more to the geometry of 2-dimensional spherical surfaces. In the adjoining figure, let K be the spherical surface touched at S by the plane E, which for facility of presentation is shown in the drawing as a bounded surface. Now, let L be a disk on the spherical surface. Now let us imagine that the point N of the spherical surface, diametrically opposite to S, there is a luminous point throwing a shadow L of the disk L upon the plane E. Every point on the sphere has a shadow on the plane. If the disk on the sphere K is moved, its shadow L on the plane E also moves. When the disk L is at S, it almost exactly coincides with its shadow. If it moves on the spherical surface away from S upwards, the disk shadow L on the plane also moves away from S on the plane outwards, growing bigger and bigger. As the disk L approaches the luminous point N, the shadow moves off to infinity and becomes infinitely great. Now, we put the question that the laws of disposition of the disk shadows L on the plane E. Evidently, they are exactly the same as the laws of disposition of the disk L on the spherical surface. For on each original figure on K, there is a corresponding shadow figure on E. If two disks on K are touching, their shadows on E also touch. The shadow geometry on the plane agrees with the disk geometry on the sphere. If we call the disk shadows rigid figures, then spherical geometry holds good on the plane E with respect to these rigid figures. In particular, the plane is finite with respect to the disk shadows, since only a finite number of the shadows can find room on the plane. At this point, somebody will say, that is nonsense. The disk shadows are not rigid figures. We have only to move a 2-foot rule about on the plane E to convince ourselves that the shadows constantly increase in size as they move away from S on the plane infinitely. But what if the 2-foot rule were to behave on the plane E in the same way as the disk shadows L? It would be impossible to show that the shadows increase in size as they move away from S. Such an assertion would then be no longer have any meaning whatever. In fact, the only objective assertion that can be made about the disk shadows is just this, that they are related in exactly the same way as are the rigid disks on the spherical surface in the sense of Euclidean geometry. We must carefully bear in mind that our statement as to the growth of the disk shadows as they move away from S toward infinity is in itself no objective meaning. As long as we are unable to compare the disk shadows with Euclidean rigid bodies which can be moved about on the plane E. In respect of the laws of disposition of the shadows L, the point S has no special privileges on the plane any more than on the spherical surface. The representation given above of spherical geometry on the plane is important for us because it readily allows itself to be transferred to the three-dimensional case. Let us imagine a point S of our space and a great number of small spheres, L, which can all be brought to coincide with one another. But these spheres are not to be rigid in the sense of Euclidean geometry. Their radius is to increase in the sense of Euclidean geometry when they are moved away from S toward infinity. It is to increase according to the same law as the radii of the disk shadows L on the plane. After having gained a vivid mental image of the geometrical behavior of our L spheres, let us assume that in our space there are no rigid bodies at all in the sense of Euclidean geometry, but only bodies having the behavior of our L spheres. Then we shall have a clear picture of three-dimensional spherical space, or rather of three-dimensional spherical geometry. Here our spheres must be called rigid spheres. Their increase in size as they depart from S is not to be detected by measuring with measuring rods any more than in the case of the disk shadows on E, because the standards of measurement behave in the same way as the spheres. Space is homogeneous. That is to say, the same spherical configurations are possible in the neighborhood of every point. This is intelligible without calculation, but only for the two-dimensional case. If we revert once more to the case of the disk on the surface of the sphere, our space is finite because, in consequence of the growth of the spheres, only a finite number of them can find room in space. In this way, by using as a crutch the practice of thinking and visualization which Euclidean geometry gives us, we have acquired a mental picture of spherical geometry. We may without difficulty impart more depth and vigor to these ideas by carrying out special imaginary constructions. Nor would it be difficult to represent the case of what is called elliptical geometry in an analogous manner. My only aim today has been to show that the human faculty of visualization is by no means bound to capitulate to non-Euclidean geometry. That was a long piece. So yeah, Einstein talking about a number of things there, especially within regards to his theory of relativity, the attraction of mass, and the idea of whether space is finite or infinite. It is now pretty much agreed by most in the scientific community that it is infinite, because we are forever expanding. It is believed, at least, that the universe is continuing to expand, so they believe it is also infinite. Einstein did believe that it is finite, though his theory would prove it wrong. And it is something that he came in conflict with a number of times. But yeah, So we are, he's saying you cannot really measure the universe as a rigid structure because it is constantly expanding. It is infinite. Or so it is believed by many. He also talks about the theory of relativity in a way, give an example of an object, a sphere, located above a plane, and a separate light source. The sphere casts a shadow on the plane because of the light source. When the object moves, as the light source sits still, the shadow of the object moves with it. So, and he also shows that as the object moves up, the third dimension, up and down, because the two dimensions are back and forth and side to side. But yeah, he's trying to represent how it would work, the idea would work in a three-dimensional scale, while also trying to give us a better look at a use of geometry, that not everything is set to Euclidean, which is more of a fundamental form, I would say, of geometry, because it requires rigid structures and everything. But yeah, as always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.